Great. Good morning. I hope you had a nice evening. It's as I said yesterday, for us it's a major challenge here to introduce a number of topics that are considered quite complex. But based on especially to the questions that you have asked yesterday to our keynote speakers, I think that the level of the audience is quite high. So let's take this chance and take the challenge and see what we can really learn from this process, from your side, but also from our side, because also for us it's an experiment. It's an experiment where we would like to demonstrate how, when we expose students to quite complex topics, we believe that we are supporting significantly the development of key skills. So I will try to, in my presentation for the next hour, I will try to introduce the different topics related to the effort we are making to come as close as we can to Big Bang, to the start, let's say, to the birth of the universe. And as we are here in Thessaloniki, in the capital of Macedonia, I thought that we have to pay some tribute to Democritus, who lived and worked not very far from here, about 200 kilometers in Avdira, in Thrace. And he was the first who introduced the idea of atom. And he had really this concept that everything consists of atoms and empty space. So in my presentation, I will try to convince you that the empty space has much power. In fact, it has more energy than the space as we know it, and the matter. So I will try to introduce a discussion because I would like to have this interaction with you. So I would like to ask you what these two pictures are presenting. Yes, please. Yes, you. Yes, you. It's a supernova. Do you know what a supernova is?
It's like when stars die of their cycle, it's that star. They go out to bang, and after that there's material left, and that material can turn into like core for neutron star or black hole.
Great. So, as it was presented in one of the keynotes yesterday, the star is a nuclear machine, and it produces nuclear energy. On the other side, the gravity is pushing everything to the center. So when the fuel is consumed and the star is approaching the end of its life, because of gravity, is going to collapse. And if the star is big, much bigger than our sun, it collapses in such a way, with this big explosion that is called supernova. There are two pictures in the screen. There is, this is the first one, and here is the second one. Can you tell me what is the timing? Which is the taken first, according to your view? Yes? This is first, and this is second, you think? Okay, and how we have managed to do that? Okay, so what, in principle, this event was observed in February 1987 from Australia. although it was February, it was a very nice summer night in Australia at the southern hemisphere. So the telescopes were observing the night sky, and they have seen this this unique event. So as they didn't have any idea when this event is going to happen, then they went back to their archive and they found the star that was exploded. Okay? So this is first and this is second. There are many more things. I mean, we can spend the whole hour of this lecture discussing about this picture. So another very important aspect here. This explosion took place at the Large Magellanic Cloud. It's a companion, a small, let's say, satellite galaxy of our galaxy. It is located at about 160,000 light years away. Is everybody okay with the term light year? I know that there are some let's say, students from the first class of gymnasium. Is everybody familiar with the term light year? Are you okay that I'm measuring the distance in light years? Everybody? Okay. So that means that when the first humans were walking on the planet, this star exploded. And the light was traveling for 160,000 years to reach our planet. Okay? So when we are looking the sky, what we see? A picture of past. Okay? Even when we are looking our sun, the picture is 8 minutes old. So we see the sun as it was 8 minutes ago, not now. Okay? So when we see the sky, we see the past. And by looking the past, we are trying to understand how the universe is developing, how it is evolving. And based on that, we are making numerous observations of, for example, similar stars like ours, and that's why we know our future. Okay? But we as humans, because humans want to know everything, how far do you think we have to reach? How far we would like to see in order to know everything? How far we have to travel in the past? 14 billion years. So we would like to see the start of everything. We would like to see the Big Bang. And this is the major research issue this moment, to reach the Big Bang. During the summer school and during also the other lectures, we will present to you, in principle, 4 topics that are related with 4 Nobel Prizes that were awarded the last 15 years. The first one of them, this was awarded in 2011. It was a study that by studying this kind of remnants, this kind of dead stars, the supernova remnants, we are able to see that universe is expanding by a bigger and bigger speed. So it's accelerating. And it is not we are not able to understand why the universe, after almost 14 billion years, keep expanding in such a high speed that is also increasing. So experimentally, this was a theoretical issue, but experimentally, this was proven back in 2011. And the Nobel Prize was awarded for this purpose to 3 American researchers who, by studying this supernova, they managed to provide evidence, experimental evidence, that the universe is expanding in an accelerating mode. And how we are doing that? We are making images of the deep sky, because this supernova was just in our neighborhood. It was very, very close. But we would like to see supernovas that are located very far away, to other galaxies in the deep sky. So how we are doing this? This is the process. We making pictures of the deep sky, and we see we are taking images like this one. These are galaxies here. These are galaxies. And we are measuring the amount of light that exists on each photo. And suddenly we see that in this photo there is more light. And we assume that this light is coming because of such an explosion, such a big explosion. So we believe that in this galaxy here, there is a supernova. So we are collecting data, and we are just removing the background. So here, this picture is the outcome of removing, let's say, from this picture, the background. So then we are able to see the supernova. In fact, this is a very similar event like this one. But this is much further away. And by studying these supernovas, we are able to see this accelerating process in the universe. And other examples. Here, it's much closer, so we can have a clear view of the supernova that exploded at the limit of this galaxy. So this is the difference image, and this is again a supernova. So in the same process, in the effort astronomy, conventional astronomy is doing, of course we had to improve the instruments, we had to install, let's say, telescopes high on the mountains in order to have a clear view. Again, the atmosphere was creating problems, so we have sent the telescopes to space. We have much more advanced telescopes, Hubble, James Webb now, and we are able to see further and further away, approaching the Big Bang. And it's very interesting because about 2 years ago, thanks to the technology, but also to nature, we were able to make an image of a star that it is located very, very far away. In principle, we will not be able to see the star. But because of a natural effect, we were able to see it clearly. So this star, Earendel means the first light. This is the name that was given. Exists about 900 million years after the Big Bang. Okay, it's a period immediately after the Dark Ages, as we will discuss in a few moments. And we were able to see it because of gravitational lensing. So this is the picture here. Again, a picture from the deep sky. And here we can see a line, a red line in principle. This is because these galaxies that they are here are bending the time-space. And because of this bending, they are creating a gravitational lens, a magnifying lens. Imagine that in this picture, we have in this point a magnifying lens. And there, at the edge of the lens, we are able to see this star. So it's, of course, the significant improvement of technology with the unique James Webb telescope, but also it's a matter of luck that this star was at the exact position in order to be magnified about 4,000 times in order to be able to see it there at the limit of the magnifying lens. So this star is very far away. Okay, so this is the process of gravitational lensing. And here, this, by the way, the slides of the presentation includes numerous links and so on. All of them will be available to you on the website, so you can click all the links and collect all the information that you have. Here, it demonstrates the effort that we have made to locate stars that are far away. I mean, in this effort of conventional astronomy. But let's say with conventional astronomy, we are finally approaching a closed door. And this door is this, let's say, soup, cosmic soup, as it was presented yesterday in the keynote talks, where we are not able. So here the universe is not yet transparent, and we cannot use light to see behind this limit. So our efforts stop at about 380,000 years after the Big Bang. And just to understand, let's say, these numbers, because we are using these numbers and sometimes, okay, they are impressive, but it's important to understand the overall view. I mean, what this graph demonstrates, it's part of a balloon. The universe is growing. We are, let's say, currently located here in a very thin line at the end. This is the present. And here is all the past of the universe. It's 13.77 billion years. So just to understand the limits of that, let's suppose that we will transform this for a moment to 1 year duration, okay? Let's suppose that about this time interval is about 1 month. So we have 12 months. Here is the first second of the first day of January. And here we are on the 31st, the last second of 31st of December of the year. When do you think Earth was created? In which month? 25th of December. Please remember, yesterday there was a discussion that the Earth is about 5 billion years. 5 billion years old. 5 billion years. So in principle, I have to move about 5 months. So Earth is created at the end of August. Earth is created and the solar system is created at the end of August in 12 months duration. The dinosaurs are walking on the planet during Christmas, 25th of December, okay? And the humans start walking on Earth after the 23:54 of the 31st of December. So we have about six minutes of life in the framework of the universe evolution. Okay? Is it clear? Sure? So, this star, the star that we found, is about here. The star is about here. Maybe I can take this one. Okay. So, the star Eridel is about here. So, the universe was very hot. It was like I have a big can and the soup is very hot inside. And suddenly, I'm throwing everything on the floor, and as it's expanding, it's becoming colder. And then it's becoming transparent. And then we can see. Okay? And it takes some time, we call them dark ages, till the formation of the first stars. The first galaxies, and so on. And then it's expanding. Look at this point here. This is the acceleration that I was talking about. So it's becoming faster. In the beginning, we said it expanded very fast. Then it became, let's say, to a constant speed, and now is accelerating again. And this is what we said yesterday. We have no idea why this is happening. So our effort from here, from this point, from these 6 minutes of life of the evolution of our civilization, we want to see back here. Okay? It's a major challenge. It's a major challenge. And I believe that this is going to be the challenge also for some of you who want to follow, let's say, a scientific career in the field. So the conventional astronomy cannot work. We have 3 different ways to approach this issue, to see in this cosmic soup. Okay? Because it's very crucial here. It's very crucial to understand all these points, because this is the key to understand how the universe is possible to expand continuously with an accelerating speed. As it was discussed yesterday, everything we see, the stars around us, everything, consists of matter, that it is about 5% of the total energy that was released with the Big Bang. About 25% is the dark matter. It behaves like matter, but we don't know which particle is associated with. We understand, as you heard yesterday, that because of the rotation of the galaxies, the rotation speed of the galaxies, it must be additional mass in their structure that we are not able to see. So we have experimental evidence of dark matter, but we have not managed yet to identify the particle that is really responsible for carrying it. And there is about 70% that is causing this expansion, accelerating expansion of the universe, for which we don't have any idea. In principle, it looks like when the distances between the stars, between the objects, is becoming very big, the gravitational force has the opposite impact. So it's pushing the masses away. So the power of empty space is more significant than the power of matter. This is the graph that was presented also yesterday with more accurate results and data that we are getting from different experiments. So let's make a small video break, let's say, to see the picture of our universe. This video was created back in 1977 from IBM, and we really prefer to show this video because it presents the evolution also of the scientific inquiry. I think, again, we have some problem here with the... Okay.
The picnic near the lakeside in Chicago is the start of a lazy afternoon.
We will see a couple having picnic
We begin with a
next to the
scene 1
Chicago
meter
lake.
wide, which we view from just 1
And
meter
every
away.
10 seconds,
Now, every 10 seconds, we will look from
the
10
window that
times
we
farther
see
away,
will
and our
increase
field of view will
10
be 10
times.
times wider. This square is 10 meters wide, and in 10 seconds, the next square will be 10 times as wide. Our picture will center on the picnickers, even after they've been lost to sight. 100 meters wide. The distance a man can run in 10 seconds. Cars crowd the highway. Powerboats lie at their docks. The colorful bleachers are Soldiers Field. This square is 1 kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on the lake shore. 10 to the 4th meters, 10 kilometers. The distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake. 10 to the 5th meters. The distance an orbiting satellite covers in 10 seconds. Long parades of clouds, the day's weather in the Middle West. 10 to the 6th, a 1 with 6 zeros, 1,000,000 meters. Soon the Earth will show as a solid sphere. We are able to see the whole Earth now, just over a minute along the journey. The Earth diminishes into the distance, but those background stars are so much farther away that they do not yet appear to move.
During the presentation, I will come again and again to the issue of empty space. Look this picture as it is developing. The Earth in there and the empty space around it. So
now
this is the
small part of the path,
the path
the Earth moves about
of the Earth moving
now,
around the Sun.
The neighbor planets, Venus and Mars,
closest planets.
then Mercury. Entering our field of view is the glowing center of our solar system, the Sun, followed by the massive outer planets, swinging wide in their big orbits. That odd orbit belongs to Pluto. A fringe of a myriad comets too faint to see completes the solar system. Ten to the 14th. As the solar system shrinks to one bright point in the distance, our sun is plainly now only one among the stars. Looking back from here, we note 4 southern constellations, still much as they appear from the far side of the Earth. This square is 10 to the 16th meters, 1 light year, not yet out to the next star. Our last 10-second step took us 10 light years further. The next will be 100. Our perspective changes so much in each step now that even the background stars will appear to converge. At last, we pass the bright star Arcturus and some stars of the Dipper.
Now the stars in the background start moving.
Stars
so the distances are so big that we can see
galaxy.
A bigger structure, which is our galaxy.
Giant steps carry us into the outskirts of the galaxy. And as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk. The 2 little satellite galaxies of our own are the clouds of Magellan. 10 to the 22nd power, 1,000,000 light years.
Now what we see are galaxies.
Bring a new level of structure
if
to
they
the
are
scene.
not stars anymore.
Glowing points are no longer single stars, but whole galaxies of stars seen as one.
We will see some galaxy clusters, like the one that deviate the light in order to be able to see this star that was located so far away.
This lonely scene, the galaxies like dust, is what most of space looks like. This emptiness is normal.
This is the
richness of our own neighborhood is the exception.
The picture of the universe as
the
we
trip
have
back to the picnic on the lakefront.
Now we will do the opposite. We will go very fast by dividing the window every time.
In each 2 seconds, we will appear to cover 90% of the remaining distance back to Earth. Notice the alternation between great activity and relative
So
inactivity.
from very large scales, we will go to nanoscales.
A proton in the nucleus of a carbon atom beneath the skin on the hand of the sleeping man at the picnic. the 9th meters, 10 to the 8th, 7, 6, 5, 4, 3, 2, 1. We are back at our starting point. We slow up at 1 meter, 10 to the 0 power. Now we reduce the distance to our final destination by 90% every 10 seconds, each step much smaller than the one before. At 10 to the minus 2, 1/100th of a meter, 1 centimeter, we approach the surface of the hand. In a few seconds, we'll be entering the skin, crossing layer after layer from the outermost dead cells into a tiny blood vessel within. Skin layers vanish in turn. An outer layer of cells, felty collagen. The capillary containing red blood cells and a roughly lymphocyte. We enter the white cell. Among its vital organelles, the porous wall of the cell nucleus appears. The nucleus within holds the heredity of the man in the coiled coils of DNA. As we close in, we come to the double helix itself, a molecule like a long twisted ladder whose rungs of paired bases spell out twice, in an alphabet of 4 letters, the words of the powerful genetic message. At the atomic scale, the interplay of form and motion becomes more visible. We focus on one commonplace group of 3 hydrogen atoms bonded by electrical forces to a carbon
We are
atom.
entering now to the sea of the electrons that they are around the nucleus, and we are getting a quite similar picture. Again, empty space. The atom is in principle
Now we come upon the 2
empty
inner
space.
electrons held in a tighter swarm.
And there in the center,
As we draw toward the atom's attracting center, we enter upon a vast inner space.
we are locating the
At
nucleus.
last, the carbon nucleus. So massive and so small. This carbon nucleus is made up of 6 protons and 6 neutrons. We are in the domain of universal modules. There are protons and neutrons in every nucleus, electrons in every atom, atoms bonded into every molecule out to the farthest galaxy. As a single proton fills our scene, we reach the edge of present understanding. Are these some quarks in intense interaction? Our journey has taken us through 40 powers of 10. If now the field is 1 unit, then when we saw many clusters of galaxies together, it was 10 to the 40th, or 1 and 40 zeros.
So, is it possible really to study the first moments after the Big Bang by looking to the microcosmos? Maybe yes.
You can see the stars, but they were all of years before. And you can see how much time does the universe made.
In principle, we are developing technology to cover all these areas, let's say, from galaxies till the basic structure. Because in the first moment, if we want, let's say, the first approach to see the Big Bang is in principle not to see it directly, but create the conditions immediately after the Big Bang. And in order to do that, we have to give to the particles so big energy in order to see, let's say, their components, what they are consist of. And to do that, we are using accelerators. We have to give to the particles the very big energy they had the first seconds after the Big Bang. This is how we are trying to approach this issue. And it seems for the moment to be the most successful approach. How we can do that? Now we are not using telescopes, but we are using accelerators. We are moving 150 meters under the ground, and we are installing a very big experiment, a very big, I would say, particle highway. It's about 27 kilometers long, and we are using it to accelerate particles, to reach very high speeds, to reach very high energy, and in this way simulate how the particles were colliding in this cosmic soup. After the first seconds after the Big Bang. And this is what we are doing. This is the most complex human machine. I don't know if you had the opportunity to visit. Usually schools are organizing visits to CERN, and students have the chance to visit this infrastructure. So we will see how difficult in principle is to give such big energy to the particles. And we have this complex system to do that. Let's see another video here to introduce the issue. So everything starts from the atoms of hydrogen. We have to remove the electron, and we will accelerate protons.
Culminating in CERN's spectacular Large Hadron Collider.
It's very difficult to create a linear accelerator. It has to start from Moscow and go to LA in order to manage to get such high speed. So we are going to use rings. And every time the particles are making a cycle, we are giving them an energy kick. And they are increasing their speed. Let's see how this is happening. So these are protons. These are protons. Accelerated
this
in
acceleration has caused Lina 2 to be likened
in a
to the
tube, in a
lumbering
linear
first
tube,
stage of a huge
in the first
rocket.
step of the process that is taking place at CERN
It'll be
in
traveling
Geneva.
at 1/3 the speed of light.
So at this point, they have 30%, 33% of the speed of
light. In order
light.
to maximize the
we would like to approach
the packet
speed
is divided
of light.
up into 4, one for each of the booster's rings.
So we cannot accelerate them immediately, so we have to go step by step as we are going in the car, and we are setting the first speed, the second speed, third speed, and so on.
Repeatedly
so we are creating these packages, these bunches as we call them, of particles, and we are accelerating them.
Magnets exert a force on the passing protons.
The magnetic field is crucial here to keep the particles
so powerful electromagnets
turning.
are used to bend the beam of protons round the circle. The booster accelerates the protons up to 90.
We can reach a limit. We are not able to give more speed because then they are going to hit the wall and we will lose everything. So we have to move to a bigger ring.
It's then flung on into the proton synchrotron, by analogy, stage 3 of our rocket. Let's just follow 2 such proton packets. The proton synchrotron is 628 meters in circumference.
The blue is just because we are going to separate the particles, protons moving to the opposite direction in the highway later. So it's still protons, but we are using the 2 different colors to demonstrate that we will separate them later.
Field cannot translate into increased velocity.
So they are already at some point that they cannot increase their velocity anymore.
The added energy manifests itself as increasing mass of the protons. In short, the protons can't go faster, so they get heavier.
They're becoming
the microscopic kinetic energy of each proton is measured in units called electron volts.
When we started, it was like having a small lamp moving it around. Now we have a whole
the protons are now 25 times heavier than they are at rest.
Heavy. Now,
the packets of protons are now channeled into stage 4.
In principle, what we would like to do is we would like to bring the particles in the conditions
to accept protons
as they were the first moments after the Big Bang, and to create these collisions.
Soon, the packets of protons will be energized sufficiently to be launched into the orbit of the gigantic Large
So now it's time to enter this particle highway to the Large Hadron Collider.
And straddles both France and Switzerland. Lying deep underground, it has a circumference of 27
kilometers circumference with the speed of light. how many times they are making their cycle in 1 second. There is 1 missing, 1 0 missing. Yeah. So, you want to say something? 12,000 times. Μπράβο, Φίβο. Μπράβο. Πολύ ωραία. 12,000 times per second. 12,000 times per second. And we are doing something that we wouldn't be allowed to do in a highway where the cars are moving. We are creating 4 junctions, 4 points that we are going to... Oh, I lost the sound.
Clockwise. The counter-rotating beams cross over in the 4 detector caverns, so they can be made to collide.
We are pushing them to collide. The tube has this size,
and it's the debris from these
and it's full of protons.
Trapped in the detectors.
Still, most of the protons are going to cross each other without understanding the existence of the others.
808 packets.
Because again, we
During
have
this time,
a
the
complete
LHC adds
space
extra
here.
energy to each proton,
Still,
whose
we will
velocity
manage
is now
to have some
near the
collisions.
speed of light that it goes round
And
the 27
we have
kilometer
to be
ring
there
over 11,000
with the
times
necessary
each
equipment
second,
to
getting
make a
boosted
photo
energy at each revolution
of this collision,
from the pulsed electric
to
field.
monitor this collision, because this is
Finally,
where we are going to
each
get the
proton
data.
has an energy of 7 tera electron volts, and they're 7,000
7
times heavier than at
electron
rest.
volts is the
magnetic
energy that
force
they are
needed to
getting.
keep the beams
And as
bending
they
to
are
the ring
colliding
is so
to the
enormous
opposite
that nearly
direction,
12,000
it means that
atoms
we
flow
have
through
a
its
collision of
electromagnets.
14 tera
This is
electron
achieved
volts.
by making the
This was
LHC
also the
colder
idea
than outer
of
space,
having the
so
particles
that its
moving to the
magnets
opposite
become
directions to
superconducting.
increase the energy
Now
of
the protons
the
are ready
collision.
to collide.
Because the higher the energy, the closer
A
we are
steering magnet
at the
finally
energies
brings
of Big
them to a
Bang.
collision course. The total energy
So this is the idea. Here are the protons, we see the quarks inside, and in principle we have the quarks, the components of the protons collide with each other. And this is the device that we have, an advanced digital camera, I would say.
And it's hoped these
quite big, 30 meters high, 30 meters in diameter. So to get information on how our universe was created.
In the future.
So this is the first technique that we have. And let me ask you a question. Let's suppose that I have 2 strawberries, 2 small strawberries. And I'm bringing them in collision. I'm giving them enough speed. Let's suppose that I have a collider where is increasing the speed of the strawberries. Is it possible to create a watermelon from their collision? 2 small strawberries, mass M and mass L. I'm creating one particle. Could it be the mass of this particle bigger than 2M?
So it could happen.
It could happen. How many believe that the mass of the resulting particle could be bigger than 2M? All the others believe that it is not possible. I will need to repeat my presentation, Mr. Burlas. So I can create a very big watermelon because the small strawberry has increased its mass, as we said. because it's moving very fast, okay? It has become, as we said, an energetic elephant. So two elephants are colliding. And this is the idea. This is how particles are created. From small ones, very high energy, very big speed, they collide and they create a watermelon that is moving not so fast, a slow watermelon. Okay? This is the idea of the colliders. So in principle, this is, a nice drawing. By the way, this was from the school book of the 3rd class of Lyceum, 17 years old students in Greece, the previous book that included this issue. And I believe it has important value to demonstrate this idea. Okay, this is the machine. You see also the side at CERN. We are trying to identify the particles. It's split like an onion in different parts in order to be able to understand, let's say, okay, here I have a track of a particle, then it interacts here with electromagnetic calorimeter, so it is a photon or an electron or a positron. If it goes through, it's a muon and all the other particles. And in this way, I'm identifying all the particles I know. And if there is something that I don't know, there are two scenarios. Either I have made a mistake, or I have found a new particle. This is the real picture, and you can see also the person here. By the way, this facility you can visit at CERN, and you can go down, especially during December and January when it is open, and it is very, very impressive. So this was the way to identify the Higgs boson. This is the second Nobel Prize that we are going to discuss in this summer school in about 10 years, 11 years ago, okay? And this is the creation here in the center. This is a picture of taken from this digital camera. Here in the center, a Higgs boson was created, and its signature are these 4 muons, because the Higgs boson, that it is responsible for the mass of the particles, is not living so much. We are not able to detect it, but we can see its signature. So when it dies, it creates 4 muons. Is one of the ways that is going to die. And by detecting these 4 muons, we are able to see that here, during the collision of the protons, a Higgs boson was created. And this was, let's say, the second Nobel Prize rewarded back in 2013 for the discovery of Higgs boson. The announcement took place on the 4th of July 2012, and we were very lucky because we had a similar summer school like this one. This was for Greek students in Crete, the day that the announcement was made. And we had a whole session devoted to that. This is how we measure its mass. It's much bigger than the colliding particles. And we were able, this is a demonstration that we can create a watermelon from the strawberries. And here are the scientific data from this discovery. I will go in the next 5-10 minutes till the end of my presentation to other 2 ways of looking and studying and trying to identify the Big Bang. Both of them are under development, so we cannot say that we have real data, that demonstrate that we can go so far. But in principle, we have the proof of concept. We have tried to get data that demonstrate that the principle is working. It's a very, very demanding process. Here you see a ship And there are some guys here, some researchers, who are looking to the bottom of the sea, and there they see the stars. Is it a bit crazy, eh? But here is another similar image. Researchers are opening holes in the ice, and they are looking there and they see the stars. In principle, this is how the process of neutrino telescopes are working. Neutrino telescopes, instead of using photons like conventional astronomy, are using neutrinos. The neutrinos have no charge, so they will not bend. They have very, very small mass. This was another Nobel Prize that rewarded some years ago related to that. And they have the unique characteristic that they can cross the mass like the light is crossing the window, the glass. So for them, the mass is transparent. From the moment I have started my talk, millions of neutrinos have crossed my body, and they have gone through the Earth to the other side of the planet. If we were able to see neutrinos, I will not be able to see you from the heavy rain of neutrinos that we are experiencing this moment. But we don't understand anything. So as we have so big number, and they are not interacting a lot with matter, it's very difficult to detect them. So there is a whole technique that we are going to discuss on Thursday on how these telescopes are working. Here I'm just going to make a short introduction. The neutrino is coming from the center of the planet, has crossed the planet. So that's why the guys on the ship or in the ice, they were looking to the other side, because the neutrino telescopes are located in the bottom of the sea, but they are looking to the other side of the planet. So we are looking, if we install a neutrino telescope here in Greece, in the ocean, we will look the sky of the Pacific Ocean, the sky of Hawaii, for example. So the neutrino is coming. Some of them, out of the millions of neutrinos that are coming, will interact with matter. It will give a muon, and the muon, when it's entering in the light, in the clean light or in the seawater, it will produce Cherenkov light. Why is doing that? Because the muon is moving faster than the light in the water. So we know that the highest speed is the speed of light, but this is in vacuum. When light is entering in the sea or in the water, it reduces its light, okay? Its speed. It reduces its speed. But the muon, moving with about 80% of the speed of light, is not going to reduce its speed. So the muon is keep traveling with 0.8 of the speed of light. And when this is happening, it's producing a blue light, a cone of blue light that is called Cherenkov radiation. And with the neutrino telescopes, we are installing these detectors at the bottom of the sea in order to be completely dark, to be able to detect this blue light. And we are able to reconstruct the track. And by reconstructing the track of the muon, we are reconstructing the track of the neutrino, and we are able to set targets in the sky. And we hope that these targets they are located much, much further away than the targets that are coming from light. One major effort took place in Peloponnese, at the southwest end of Peloponnese, at a depth of about 4,000 meters under the sea. And this is a different way of constructing telescopes. So here we are deploying a whole structure that has these optical modules, as we call them, sensors, that they are located there to see these blue light. This is one floor of a very big telescope, about 330 meters height, in order to see the light of the neutrino. So this is the construction. Here is a similar experiment, much more advanced, that is taking place at the South Pole in Antarctica. So you see, this is the size of the detector, and this is the size of the Eiffel Tower. And this is the upper part of the ice. In Antarctica, the ice is about 3,500 meters deep. They are opening holes with very hot water, up to 3 kilometers, and they are deploying these optical modules inside. This is the station at the South Pole, and this is an event. You see, all these optical modules waiting to see this blue light, and this was an event. This was announced in 2013. It was a very high energy particle. It had an energy of about 200 TeV, tera electron volt. It means it's 100 times, 200 times more energetic than the energy that we are able to give to the particles at LHC. So from where these kind of particles are coming from? They are coming from cosmic accelerators, like this one, okay? So in principle, we have demonstrated that we are able to detect neutrinos that are coming from these structures. And we hope that in the future we will develop much more advanced neutrino telescopes to see neutrinos that are able to escape the cosmic soup. And we are able to see neutrinos that they are coming from Big Bang. The third case is the observation of gravitational waves. As it was, this was discussed yesterday, so I'm not going to devote time to that. I will close just with one video. I just want to say that this is the fourth Nobel Prize that we are going to discuss in this summer school. We will have a lab exercise for you related to that in order to demonstrate. Just to remind you that 36 solar masses black hole collided with 29 solar masses black hole, and they created a 62 solar masses black hole. And this was the first event that was detected back in 2015. It was presented in 2016, and 3 solar masses of energy were released to the universe, creating these very big gravitational waves that we were able to detect. Again, as it was presented yesterday, this is a process under development, in progress, to develop bigger and bigger detectors to be able to see gravitational waves that are coming from Big Bang. Because also during the Big Bang, significant gravitational waves were created. I would like to close my presentation with a video that I think it's really a tribute to the scientific process.
Interferometer gravitational wave
from
observatory.
The key actors themselves,
LIGO
they are presenting
really
their effort.
observatories that work in unison.
I believe this is the message,
the LIGO interferometer
especially
has
for
arms that are about 2.5 miles long, 4
young people
kilometers.
who have interest in the scientific process.
The laser produces
to see how
the
difficult
purest light
is in
we
principle
possibly make. Produces
to
light that's so
turn a
coherent
theoretical
that it's
issue
capable of detecting gravitational waves.
to real and provide
very
real
massive
experimental
mirrors. They
data
weigh
for this.
40 kilograms, which is about 88 pounds. They're about this thick, and they're just the purest material you can imagine.
The NSF, of course, had to be the source of funding for anything that would be as expensive as this.
This was
received
going to be
the Nobel Prize.
a very high-risk experiment.
There is always the financing body that has to be convinced to support this effort.
In the 70s and 80s, I'm amazed at how bold it was to do this, and visionary. It was bold and visionary. There's no other way to describe it.
NSF management, the National Science Board, they had to really step up to that. And they had a lot of discussions, brought in a lot of experts. There was great debate going on. But in the end, the people who thought it could be done won the day, and they went after it.
Gravitational waves were predicted by Einstein about 100 years ago, and they are dynamical perturbations in the fabric of space-time, ripples in space-time, if you will.
A ripple in the fabric of space and time, the same way as a ripple on a pond is a ripple in the shape of the surface of the water.
Nobody really believed that you could ever detect them because the size of the effect is so small. 1,000th the diameter of a proton.
Even Einstein himself never thought a detection would be possible.
I tried to do this back in the 1960s when I was a student. We couldn't make any progress. We didn't have the technology.
The idea was extremely simple, and it turns out to be the basis of LIGO. What the gravitational wave does is it stretches space this way and compresses space that way. So you exploit that property.
Weiss is the second
One
person
object
that
here
received the
and
Nobel
another object
Prize,
over there,
and he
and let the
demonstrates
gravitational
how
wave go
simple
through that
ideas,
system,
basic
and it'll change
ideas,
the space
can
between
change
these by contracting that one
the
and extending that
process,
one.
The way
And I came to
that
the
we are
conclusion
thinking.
that if you
so
make this long
we are
enough,
looking as
if you didn't make it a little
the director of
like
the
this, but you
American
made it sort
Farm
of
School
kilometer scale,
said
you could probably
yesterday,
get these
for
extremely
people who are
precise
going to
measurements.
ask the correct questions. This is what
Nobody had ever
the
made
answers
something
we
like
have
this before, so there was a lot
we
of
need
technological challenges that
the
needed to
correct
be
questions.
overcome.
We need the people who are going to think out of the
It
box.
was just amazing, mind-boggling.
The MIT group has typically concentrated on developing new techniques to make the instruments work, and then to work on also data analysis algorithms that are well informed by the understanding of the instrument.
We have observed gravitational waves from two black holes forming a larger black hole.
Two black holes merging together, literally nearly the speed of light, to produce a bigger black hole. How cool is that?
I said, holy mackerel.
Well, this is the beginning of a whole new way of studying the universe.
It's monumental. It's like Galileo using the telescope for the first time.
Every time we have pointed a new instrument into the sky, nature has revealed secrets to us that we haven't known before. And so I feel very confident that this is just the beginning of such an era for gravitational wave observations as well.
Who knows what we'll see?
I would love to see Einstein's face if he could read this article that we just put out. I mean, he would have been as dumbfounded as we are, because it's a wonderful proof that all of this incredible stuff, the strong field gravity, is in his equations. Just imagine that. To me, that's a miracle that that happened. Man's thinking, and also all the elegance, not only in the theory, but the elegance in the experiment. I mean, that is a human endeavor that I think everybody in the world should be proud of. I had to tell you that.
So, thank you. Questions?
In the picture with...
Yeah, I'm going to do that.
there.
Nene.
It's left gravitational wave or a right gravitational wave? It's left from that or right from that?
What do you mean? The picture you said about the star, no?
Yeah.
This is not a gravitational wave. This is...
Yeah,
This is light. Here I'm speaking still for the conventional astronomy and the efforts we are making in order to see as far as we can. Okay? So, imagine this is the deep space. And this is the limit I can see. And suddenly, it's a natural phenomenon, natural phenomenon. It's not a technique. It has nothing to do with technology. Here, because of these galaxies, the light that is coming behind, maybe this star is behind these galaxies, so we will never be able to see it, but the light bends. So I'm able to see not only behind these galaxies, but also further away, because it's like putting a magnifying lens in my optical field. So I can see more clearly and further away. And then, again by chance, because it happened, this is the pictures of the galaxy. I'm not able really to see any star there, but there, because of the location of this star, I was able to see it. So this is not a gravitational wave. Gravitational wave is a completely different thing.
Yeah.
I need a completely different detector in order to see that. We will have a whole lab in the next days to see exactly how we are working. But this is light. This is light. Okay?
Yeah.
Perfect.
Thank you very much.
Yeah. Could there theoretically be an application of high-energy neutrinos in particle accelerators? And if that was possible, what results could that produce, theoretically?
You mean to produce neutrinos at a particle accelerator?
Yeah. No, I mean to, for example, we saw previously that high-energy neutrino was detected in Antarctica.
Yes.
And that could these neutrinos theoretically be used for particle accelerators? Because you said that it was, I think, about 100 times stronger than the force applied in particles in the Large Hadron Collider.
In principle, neutrinos are produced at accelerators.
Yes.
So also at CERN, it's a great source of neutrinos. By the way, there is a great experiment in Gran Sasso. So we are shooting neutrinos from CERN to Gran Sasso in Italy. So the principle is exactly this. The cosmic accelerators are producing neutrinos. Okay? So the issue is at CERN, we know exactly where the neutrinos are coming from. But with the cosmic accelerators, we are trying to create a completely different map of the sky and see the sources of neutrinos. With light, this is very easy because we know immediately that this is a source of light, another source, another source. With the neutrinos, we have to create a new map with the neutrino sources. Okay? And we expect that the higher neutrino, the most energetic sources will be the black holes. So in principle, if we put the two maps together and we have a map of the sky taken by telescopes, the more advanced telescopes, at the centers of the galaxies, we will see all the black holes. All the points that are missing in our conventional map will be filled in with a neutrino map.
Yes. Thank you very much.
Okay? This is the idea. This is, let's say, you mean these ones?
Yeah.
These are just some images. Usually these stars, these very big stars, have a companion star. Okay, so the idea is, this is not clear yet because this is very new data, that we are not only able to see the star, this very far star, but maybe we are able to see its companion. But this is still under investigation.
So those two are like less important than the main one?
Yep. Okay, so we have let's say 5 minutes break, and we can start with the next presentation. No. It's there is a small break now. Okay. And I'm here if there are further questions. More than happy to answer. I just want to say that for the neutrino telescopes, there is a whole session on Thursday. So we will explain the technique. And then there is also a workshop where we will introduce the photoelectric effect that is really combined with the technique of discovery of light that is coming from these detectors. And for the gravitational waves, we have again a lab exercise on Thursday and on Friday in order to get introduced in this detection technique. Okay, so 5 minutes break. We will revisit this. Please come back in 5 minutes for the next presentation.
Ναι. Άμα χρειάζεται την υποδίκη, πάρτε το για την άκρη. Αυτό.
Α, οκ.
Αλλά υπάρχει και στικάκι για το...
Ναι, το ακούω. Ναι. Τα έβγαλα κατευθείαν, οπότε ξέρω ποια είναι.
Εγώ να το βάλω άμα είναι. Να το βάλω. Ωραία, μπήκε. Έβαλα τον ήχο. Κάπου να βάλουμε το φέτε το στεκάκι να βάλουμε το... Είμαστε και να κάνουμε παίζει.
Ναι. Ναι, θα το βάλω.
Χωρίς ήχο είναι?
Χωρίς ήχο θα το παίξω αυτό. Θα παίξω ένα άλλο με ήχο. Είναι μέσα στο PowerPoint όμως, δεν είναι YouTube.
Μέσα στο PowerPoint και αυτό αν αλλάζει.
Ναι, θα το δω. Ναι, το... Δεν χρειάζεται, τα λέω εγώ.
Ναι.
Μου άρεσε πάρα πολύ, Αλέξης. Μπορείτε να μου το γράψετε.
Βεβαίως, με πολύ χαρά. So, the next presentation is focusing on our sun, its activity, and the impact it has to our planet. So it includes a detailed description of the processes of the sun, the process of how the energy of the sun is transferred to our planet, and the effects on our planet. So I think also at the end there is some invitation to some activities for you to be involved in the process. Eleftheria Soteriou from the National and Capodstrian University of Athens has the floor.
Hello everyone, and thank you to the organizers for the invitation. My name is Eleftheria Soteriou, and I am studying physics in the National and Capodstrian University of Athens. After I chose to direct my studies to astrophysics, I found my favorite course there, which was solar and space physics. And I am currently doing my bachelor thesis with Professor Ioannis Daglis on this field. It still is work in progress, but I am here today to share some parts of this work. Solar and space physics is basically research on solar system bodies. But for my presentation today, we will emphasize on the Sun, the Earth, and their interaction with each other. Hopefully, by the end of my presentation, you will have a better idea of how a phenomenon like this, the aurora, is created. This is a picture taken from here in Greece, close nearby in Ceres, in November. And here a picture from Germany of the aurora, and here one from Iceland. Before we start, I have a question for you. It was kind of spoiled yesterday. So here on Earth, we know that an Earth day lasts 24 hours, which is basically equal to the time needed for Earth to complete one rotation. Do you have any ideas how a Sunday lasts? In other words, the time that the Sun needs in order to complete one of its rotations. Okay. – 27 days. Okay. Yes? Sorry, 50 days. Yes. Okay. Okay, that's great. So it is up to the place on the Sun's surface. As you probably know, the Sun is not solid, so its rotation is differential, as we call it. If we are around the equator of the Sun, then one rotation lasts 25 days, close to 27. But if we are around the poles of the Sun, it takes 10 days longer for the Sun to complete one rotation. Let's now talk about some more general characteristics of the Sun. As you can see from the first picture here, its diameter is pretty big, and if we put many Earths there, we would need 109 Earths in order to fit to the diameter of the Sun. Its mass is 333,060 times the mass of the Earth. The maximum temperature reached inside the Sun is in its core, and it's about 15 million degrees Celsius. And our Sun is 4.6 billion years old, and it's supposed to live for another 4.6 billion years before it dies, as you also heard yesterday. Another important information before we move on from this slide is that the distance between the Earth and the Sun is 150 million kilometers, and as you also heard before, the light from the Sun needs 8 minutes to travel this distance and reach our eyes on Earth. Now let's talk about the anatomy of the Sun. First of all, nowadays basically the Sun consists of hydrogen and helium, and we will divide the Sun in two large parts in order to talk about it a bit more easily. So we firstly have the interior of the Sun, its inside, which is not visible to us at all, and then we have the outside of the Sun, which is the only part that we can actually see. Starting from the inner part of the Sun, we firstly have its core in the middle, as you can see here, where hydrogen's combustion into helium takes place, and this is how energy is generated there in the form of light and heat. This energy generated in the core is traveling at first through the radiative zone via radiation. This is why it's called the radiative zone. But moving outwards, it reaches a point where it can no longer be transferred via radiation. And this is the convective zone. As you can probably imagine, the closest we are to the core in this zone, so the inner part of this zone, has higher temperatures than the outer part of this zone. This is why hotter plasma is traveling from deeper areas of this zone closer to the surface of this zone. And those that I just described are called convective currents. As you can see with the arrows here, it's just the motion that I described. And because of this circular motion that the plasma is doing there, they are called convective cells. Next, well, in this zone here, due to these convective turbulent motions, and also due to the differential rotation of the sun that we talked about, happens the generation of the solar magnetic field. Sorry. Okay. We now turn to the visible part of the sun. Firstly, the photosphere of the sun is what we can actually see as the sun's surface. Followed afterwards by the chromosphere, where a dramatic decrease of the density of the plasma takes place. The transition region afterwards connects the chromosphere with the corona. And then the corona, well, if you have ever seen pictures of a total solar eclipse, then the corona is the only part of the sun that is visible during that time. There are also satellites and spacecrafts currently orbiting or observing the sun who have this telescopical attachment called the coronagraph. I will also show a picture later in the presentation, which basically hides the disk of the sun, well, because it's kind of blinding, and that's how we can actually see what is happening around it in the corona. Last but not least, we have the heliosphere, which ends at the so-called heliopause. Well, it's not here in the picture because it wouldn't fit in it. It reaches too far away, to the point where the existence of the sun could no longer be felt by something there. If someone wanted to travel to this point where the heliopause is, they would have to travel 123 times the distance between the sun and the Earth. And the only two spacecrafts who have achieved that goal are the Voyager 1 and Voyager 2 missions. In the surface of the sun, the photosphere, as we talked about, appear two structures that we are going to discuss. As you can see, okay, here firstly, we have the sunspots. And as you can see from the picture, they are darker spots on the surface of the Earth. This darker color shows that their temperature is really low compared to the other parts of the sun. And from those sunspots, magnetic field structures emerge. And those structures, like loops, they are called prominences, like here. I also have a realistic picture of one of these so that you can see how huge this structure is. Here, the Earth is just added in the picture so that you can compare the size. It's important to mention here that this loop that you see is not the actual magnetic field line because those are invisible, but it just is the plasma, which is the hot gas with which is full of charged particles that is traveling around the line. And this is what's visible here in the picture. From observations, astronomers knew that the number of sunspots and prominences seemed to increase and decrease, and that's how they started to view it as a circle, a so-called solar cycle. Sorry again. Here you can see a collage, basically, of many pictures of the sun, taken one each year of one solar cycle, the 24th solar cycle, and the number started counting from when we actually have data in order to call them solar cycles. So here you can basically see that in the years, for example, 2014 and 2015, the sun has many more sunspots, many more prominences, and seems more active. While there, for example, 2019 and 2020, the sun seems more calm. Not so many sunspots and not so many prominences. And so I have a graph next. Please don't freak out with the graph. I will just explain the most important parts. So here on the horizontal axis, we have the year number starting from 1965. And on the vertical axis, we have the sunspot number. As you can see, every about 11 years, there seems to be a maximum here at the number of sunspots. This is how long a solar cycle lasts, 11 years. So every 11 years, we have a maximum. Today, we are in solar cycle 25. And this year and the next year is, as you can probably see, predicted to be its maximum. Let's look now at 2019, for example. Do you see it being a minimum or a maximum? Okay. What about 2014? Yes. Okay. So let's move on to the next slide, where two pictures of the sun from the years that I just asked you about are shown. The first one is from 2019, as well as you said, it's a minimum. And the second one is from 2014, as well as you said, it's a maximum. You can see the difference, I think. The prominences and sunspots are many more appearing in 2014 when it's a maximum. I also have the same picture. The previous one was in UV, and this is in visible light, so that you can actually see the sunspots, those darker spots, as we talked about in the solar maximum. Okay. So during the solar maximum, there are explosive events happening in the sun. Two of them are the most important, I would say, and we will talk about them today. Firstly, there are solar flares. And secondly, and most importantly for today's presentation, are coronal mass ejections. Yeah, they do appear here, but I will show them again in a bit. So solar flares are basically a sudden release of energy, mostly in the form of light. But in one of the first slides, we talked about how much time light needs in order to travel to Earth, which was 8 minutes. So if a solar flare happens right now in the sun, someone with the right equipment and a bit of luck may be able to see this flare from Earth after 8 minutes. It's important also to say that since it's light, it is traveling to every direction. Let's now move on to coronal mass ejections, or CMEs. These are large explosions of plasma and magnetic field from the sun's corona. This is, as I mentioned before, a coronagraph picture where the disk of the sun is hidden so that we can see only the corona and capture events like that. Since all of this plasma and magnetic field together has a mass larger than the mass of light, which is 0, it needs more time to travel to Earth and reach Earth. If it's a very fast coronal mass ejection, it takes 15 to 18 hours, very fast once again, but normally it takes 1 to 3 days to reach the Earth. Now here is a picture that probably will help you understand the difference a bit better. As you can see here, a coronal mass ejection has this loop structure, while the solar flare has no such thing. Well, before we watch the video, those two events, explosive events, might also occur together in the same region of the sun at the same time, but they are not always related. Let's watch a video now that will probably help you understand the difference even better. Okay. Δεν έχω ήχο. Είναι μέσα. Όχι όλα. Το έχω δυναμώσει. Ναι, να μην είναι σε αυτό. Θα ακουστικά μου. Shift F5. Shift F5 τώρα. Δεν θέλω να αλλάξω και το... I hope the difference was made a bit more clear by the video. So now let's leave the sun for a bit and return to our planet. Earth has a huge shield, as you can probably also see in the background here, but it's easier here in this picture. And this shield, it's called the magnetosphere. Let's now imagine that inside of the Earth we have a huge magnet. Its core, it's like a huge magnet, and this magnetic field is created. As you can see, there are two places on the planet that are not really protected from this shield. And those are its poles, here. Okay. As sorry again. So this picture shows a perfectly dipolar magnetic field, but Earth's magnetic field is not exactly like that. From the day side, the side that faces the sun, it seems like the previous picture a little bit. But on the other side, a tail is formed, which is called the magnetotail. And this is the magnetic field basically extending due to solar wind far away from the planet. Solar wind is a stream of charged particles that is released from the sun's corona. Let's now, I will show you a video again that will basically explain the interaction between the sun and the Earth that we are talking about. Okay. So this video basically ends with explaining how the aurora is created, and this is why it has some clips here in the start. Everything is starting from the sun. I will repeat some of the things that I previously said so that you are watching them at the same time, because I think it helps understand more. Sorry? That's the sun, yeah. Well, what you will see, it's not really real because you see we just have like a hole here so that you can understand it better. But you will see. On the inside of the sun, as we talk about, energy is generated in its core, where the temperature is really high, and also pressure is very enormous. It's so enormous that hydrogen atoms, as you will see, are squeezed together, forming helium. And this nuclear reaction is what generates the energy inside the core. The light travels towards the core of the sun, firstly via the radiative zone, as we talked about, and then the convection zone. These currents of charged gas create a magnetic field inside of the sun. In some places, strong magnetic fields push their way through the surface, and the area around the line cools down, and this is how the sunspots appear. The plasma carried by the magnetic field drags the magnetic field further outwards, and at some point it stretches so much that it breaks, as you saw. Now, a huge mass of plasma captured in magnetic field lines starts traveling around in our solar system through space, which is what we name CME. This huge structure can travel with speeds from 200 to 3,000 kilometers per second. If it's really fast, after 6 hours, as you can see, it will reach the orbit of planet Mercury. After 12 hours, the orbit of Venus. And again, if it's really, really fast, in 18 hours, it will reach the orbit of our planet, and maybe even our planet at this point. And this is where this solar storm meets the Earth's magnetic field. As you can see, the magnetic field of the solar storm and the magnetic field of the Earth have opposite directions, as you can see from the arrows. The blue arrows are headed upwards, while the yellow arrows are headed downwards. Earth's magnetic field is always like that, but the solar storm's magnetic field, so the yellow arrows, could also have the opposite direction, viewing upwards like the Earth's magnetic field. And if that were the case, none of the following things that we're going to talk about would happen. But since that's not the case, and they are in opposite directions, let's now see what follows. The Earth's magnetic field lines on the day side break, and they reconnect with the magnetic field lines of the Sun, which now has plasma particles, high-speed particles, getting inside the magnetosphere. Now, the new lines that are formed are traveling backwards to the magnetotail. So normally there are more lines in the magnetotail, but just so that you can understand it better, they are not here right now. So those more lines that I talked about are the ones squeezed, and they will break again and reconnect with each other, accelerating those particles in those lines towards the Earth. Those particles are traveling along those magnetic field lines, and as you can see where I stopped it, they are traveling towards the poles of the magnetic field of the Earth. Okay, which are unshielded, as we talked about. There is no protection, not as much protection there. And this forms the aurora. And some videos follow of the aurora. Here is also a picture of what we just saw through this video. This time the solar storm magnetic field is with a blue arrow, and Earth's magnetic field with yellow arrows. As you can see, the lines will reconnect here with the solar storm's magnetic field and travel backwards, where they will reconnect again and accelerate the particles into the inner magnetosphere. We will move closer to the aurora and the poles of the Earth in a bit, but before that we will talk about how strong a magnetic storm could be. Of course, there are stronger ones and not the strong ones. So how do we categorize them? There are 4 observatories around the globe, and all 4 of them are efficiently away from the poles of the Earth, which are, as we said again, the unshielded areas. Those observatories are measuring the magnetic field on the surface of the Earth, And basically the relative change of these values is called the DST index. And this is what we used in order to categorize the storms from stronger to not that strong. This is a diagram here. On the vertical axis we have the values of the DST index, and on the horizontal axis we have the day of year. I chose here 10 days starting from the 10th of May, when you might have heard that there was a big solar storm happening, and also auroras in lower latitudes were visible. So starting from here, early on the 10th of May, we see that the values are around 0. So if there was no no magnetic storm happening, those values would stay this way for the whole period of those 10 days. But as you can see, during that day, there was a little increase here in the values of the DST index, which happened when the reconnection in the day side of the magnetosphere happened. And this is called the initial phase, or storm sudden commencement. This phase is followed by a huge decrease, as you can see here, of the DST index, which is happening during the acceleration of particles, which are now drifting around our planet, creating a magnetic field that is headed to the opposite side of Earth's magnetic field, and this is why it seems like a decrease on the diagram. And this is called the main phase of the storm. The minimum of the DST index down there is basically the value that shows us if it's a strong storm or not. On this day, it reached about minus 420 nanoteslas, which makes it a really strong storm. It's a G5, as I have written up there, on a scale from 1 to 5, with 5 being the strongest. So the following days, after a very strong storm like that, comes the recovery phase, when in which time the magnetic field basically tries to return to its initial normal values. 2 notes before we move away from this slide. As you can see, the 9 days here was not really enough time for this storm in order to for the magnetic field to recover completely. So here it's not really 0 yet. And the second thing is that the Earth's magnetic field is not 0. The thing that it's the values of the DST index are 0 here is because the magnetometers are calibrated around this number, so that we can only understand the change and not the real values of the magnetic field. Let's now move back to the aurora. In places with higher latitudes, the aurora seems like that. How many colors can you see here? Yes. Okay. As we saw in the video, I kind of stole a screenshot of it so that I can remind you that particles are accelerated from the magnetotail and traveling through the poles, to the poles. The atmosphere basically consists of oxygen and nitrogen. So as you will see in the workshops later this week, When a high-speed electron, this is the electron coming from the magnetotail, accelerated, and this is, for example, an atom in the atmosphere that it will meet. And when it hits this atom, the electron gets part of its energy and it's excited, as we call it. But this is, as you can see, an unstable state. So after a short period of time, this electron will return to its initial phase, and the excess energy will leave as a photon. And this is the light that causes the aurora. Starting from lower heights, electrons that enter the atmosphere meet nitrogen atoms there, and they create those two colors, or even a kind of a pink shade sometimes. Accelerated particles also meet the oxygen atoms that we talked about, and they create green colors or red colors if we are higher. Well, some of you may be wondering right now how oxygen atoms can also have us seeing green and red light at the same time. So the thing is that in order to see red, we need electrons with more energy. And that's why it's only in higher heights, because as we get deeper in the atmosphere, the atmosphere is more dense. So the electron coming inside will meet many more atoms and collide many more times, so it will lose its energy and it will not have as much energy to give to the oxygen atoms. Sorry. The lower edge of the aurora is usually about 80 to 100 kilometers, and the upper edge is usually at 250 kilometers. But in some more rare phenomena, it could reach 500 to 800 kilometers. You can also see here, in order to compare the height, the Mount Everest and an airplane. So now, I don't know, were any of you that lucky in these last huge storms to see the aurora? Maybe? Anyone? Oh, really? Okay. So now this next thing I say might disappoint you a bit. I'm sorry in advance for that. But down here, the aurora isn't really over our heads. What we actually see is the top of the aurora here, as you can see from Thessaloniki, for example. And we see the aurora created above Finland. This is why in lower latitudes only red color is visible. Okay. Here I also have, for example, a picture from different latitudes with the as shown aurora pictures, and we see that in higher latitudes we see many more colors, for example also green, and as we go down, the only color that is now visible is the red color. I also have some pictures of the aurora taken from space. And it's important to say that along this beautiful, let's say, light show that we see with magnetic storm, we can also have consequences. like interference with radio communication, GPS systems, or electricity. For example, in 1859, there was a big event called the Carrington event, and it caused problems with the technologies then in use, which was the telegraph. High-speed particles, well, this is not about solar storms, but it could also happen with solar flares that we mentioned, but we didn't keep talking about them. So, when particles, anyway, high-speed particles travel in space, they are dangerous for astronauts out there, and also even for satellites and technologies. So it's important to be able to predict, I would say, but we're not really able to do that yet when such an event will happen. So now, closing, I want to say that there is a number of citizen science projects. For example, if you're interested, you could also see here. One of them is the Aurorosaurus, where you can report if you saw the aurora, like you did, and the location that you saw it from, and some of the details, for example, if it covered the whole sky, if it didn't, if it covered half of the sky, and stuff like that. And projects like that help the scientific community to have a more accurate knowledge, I would say, about the aurora. Here is a picture, for example, from May 10th, as the diagram that I showed you before from the solar storm G5. And this is all the people that went into this website and wrote that they saw the aurora. You can see there are kind of many, but here in the Balkans we don't have that much support. So you can also visit this website, and if we are lucky enough again, but it's a solar maximum now, so maybe we will be lucky again, in order to have a storm that we can actually see the aurora from. And this is pretty much all, so thank you. And yes, and I'm here for your questions. Yes. I can't hear anything.
They predicted that that there is going to be a solar storm at I think May of 2025, and I wanted to ask if it would be true. Some scientists predicted that.
Okay, so I don't think that the prediction was about a specific solar storm, but since it's a solar maximum, there are about to be many solar storms in that time. So yeah, I don't think that it has a date or something like that, but it's really possible to happen in the next year, yes.
Previously, at around the start of your talk, I saw an infographic that said that the sun's magnetic field essentially flips every 11 years. Is this related to the solar cycle of sunspots or not? Or is this just a coincidence?
No, I don't think it's a coincidence.
And is there like any relation between the two actually or not?
I mean, I'm not really sure when exactly in those 11 years this happens exactly. I will check something that I need to know, and I will come right back to you after in the break.
Thank you.
Okay. Oh, okay. It's not talking.
What effect could a solar storm has on us if the magnetic field breaks?
Well, I have good news for you. It won't break. But if we didn't have the magnetic field, we would probably be like the other planets in the solar system with no life here. So the air would not be able, the Earth could not be able to keep the atmosphere that much, so it will fade. And you understand afterwards that it's not really, yeah.
Thank you.
But this won't happen, so.
Why Earth has a different magnetic field from other planets?
What do you mean different?
I mean, as far as I'm concerned, Mercury and Venus also have magnetic fields, just not the same as Earth's. I mean, if it doesn't affect Earth and affects the other planets, there must be something different about Earth's magnetic field.
So
do we know why
it's stronger, what you were saying, it's stronger. And it has to do with the core of the Earth, I think, because the material there is what basically is like this imaginary magnet that I talked about, and this is what is creating this stronger magnetic field. So the core is different, the magnetic field is different. We are luckier, so that's it. May I ask you too something? Where did you see the aurora from?
From my neighborhood.
Yeah, where?
Menemeni.
Okay. Any other questions? Oh, up there again. Ah, here too.
From the map that you showed us, we could see that the observatories, all 4 observatories, are close to the equator.
Yes.
Is that to minimize interference?
Yes. Okay. This is why it's efficiently, as I said, away from the poles where they are unshielded, and we could have many more interferences there, so that's why.
Okay, so I think we can have now about 10 minutes break till the next presentation, to give also some time to the next presenter to get prepared. So please be back in 10 minutes. And as we said, if there are further questions, we are here to try to answer. Just you can connect your computer. Here is the HDMI, and here if you need some.
No, I don't. No.
Very happy to see you.
Hello.
Do you have video or audio file? Do you have audio?
No.
No video?
There's some animation in the presentation.
But no audio.
No,
It's only for audio.
give something like that. Sorry. Okay. Okay, thank you.
So, now we will continue with the next lecture. Is focusing on the laws of Kepler that they govern the motion of the astronomical objects from the planets till the supermassive black holes. Correct? Yes. So we have the honor to have with us Milan Milosevic from the University of Nice, who is going to give the lecture. So, Milan, you have the floor.
Thank you. Well, we see some pictures in this slide, and at first look, probably we don't have any idea what is the connection between this planet and the center of our galaxy, supermassive black hole in the center of Milky Way. And of course, if you look at those pictures without the title of this talk, you will have no idea why they are connected. But from this talk, we know that those are Kepler's law, and you will see at the end of this talk how those bodies are connected. And as you probably all know, all laws in physics are universal. They are working here on Earth and everywhere in the universe. And here you have the answer from the question at the first talk. So what are we astronomers? We are just sitting 1 minute before the midnight on the 31st December and trying to understand what's going on during the whole year. In the last minute, because we are here, the human civilization, and the whole universe is this whole year. So we want to understand in the last minute of the year what was happening during the whole year. This is the astronomy, and we are doing it. But the first question is, how did the astronomy start? Of course, now we want to understand everything in the universe. For example, me and my colleagues are working on the period of inflation. It's 1 to the power minus 35 seconds after the Big Bang. And we want to understand what's happened then in the universe. But that wasn't the reason why people started to doing astronomy. The main idea for astronomy was to understand the place of the man in the space and time. The most important thing in astronomy was to orientate and to find any connection with the process in the sky, with process on the Earth. So the idea was to make a perfect calendar, to know where, to follow the seasons, to understand what to do with plants, how to live, and of course, orientation on the land and the sea. Sometimes we cannot, in those times especially, we cannot make a real distinction between astronomy and astrology, because the intention to understand the future from the astronomical object went so far that people want to understand the future of the person, and in that time, the future, most of all, for the kings. So this is how astronomy started. Now we, of course, know that there is any real connection between astrology and science, but we have to admit that in some way astronomy arises from the astrology. What was the main problem? If you look at the stars at night and the night sky, you can see the stars, and there is not a lot of changing there. But if you follow the stars, the sky, from day to day for multiple months, and you will see something like that. Like this. You will see some objects that are moving across the sky field. Those objects are one of the brightest objects in the sky. Those are 5 planets, and they're making these loops. And that was the reason for their name, because they wandered around the stars, and it was very hard to predict them. And those planets were the reason why people started to build an image of the universe. Those were first cosmological models. it was very easy to understand something that don't change. Okay, someone put stars somewhere and they're bright and we can see them every night at the same place, but what's happening with those planets? If you take a photo, you will see something like this, and this was a very big problem how to explain, and you must explain it if you want to understand what's going on in the stars. And the first model of the universe, it wasn't the model of the solar system, it was the model of the whole universe, because we can call it cosmological, first cosmological model, because that was everything they know at that time, was created by Aristotle and after that improved by Ptolemy. And probably you know how it worked. The Earth was in the center, or we can say the man was in the center, and everything goes around the Earth. So this was the Aristotle idea. It was a very simple one, and it was perfect. You can use only spheres, and the sphere is a perfect body because it was everything like that, but there was a problem. If you try to predict the position of the planet in this way, it was impossible. It wasn't correct. The first idea was, as I said, by Aristotle, and Ptolemy tried to change a little Aristotle model and improve it to predict the position of the planet. So what he did? At first, the Earth was at the center, but Ptolemy moved Earth a little bit. And now all those circles don't go around the Earth or the center, but they go around this equant, so-called. And there are not only one circle for each planet. There are multiple circles. First, those big circles are called deferents, and those small circles are called epicycles. But if you want to apply it to the universe, to the night sky, after some time, it wasn't correct. So first Ptolemy, and for the next 14 centuries, other astronomers added more epicycle. Here, here, and here. So they make a small corrections to fine-tune the model to the observation. We have something like since then in physics everywhere, but it was idea. It was the first, and we must say, great idea, how to improve the model to fit the observation. This was what they were doing, but there was a problem. You can add many epicycles to improve your model, but it wasn't correct. After some time, planets aren't at the place you predict. So there was a problem in the model. Fortunately, they didn't know something we call now Fourier transformation, because if you have something like this, something like Ptolemy's idea, and with a lot of mathematics that wasn't familiar in that time, you can make any orbit you like. These are some animations from these two websites. You can click on a link later, and also when you have a presentation, and see how they did it. There are a lot of mathematics in it. Probably most of you will not understand, but if you apply this method, you can get any orbit of the planet you want. So the idea was perfect, but the idea wasn't in any correlation with the real physics. So you have a good mathematical model, you can make anything, if that is a good thing for physics, but there is no any real world in this model. So if they improve the model a little bit, they can understand the movement of the planet. But if you have mathematical model, you cannot always be sure that it is related to the reality, to the physical world. Of course, you can see that this is very complicated. Even from the understanding of mathematics we have now, you have to use a computer to calculate this. But there was a more beautiful solution, very simple solution to the problem they had. What do they have to do? They have to stop the sun and move the Earth. That was the solution. You have to move from the geocentric point of view to heliocentric point of view. And if you do it, you have a sun in the center and two planets going around the sun, and there is nothing more normal than to understand these loops. Or if you read a little bit about astrology, I hope you don't read about astrology, but if you do, sometimes you can hear about retrograde Mercury and so on, and they make a long story from it, but it's nothing more than this situation where the planets are in normal position on their orbit. Heliocentric system is a very nice idea, but there was one problem, how to prove it. You can have great idea, but you have to prove it, because you saw on the previous slides that from the Ptolemy's model you can make anything you want, but we know it's not correct. Heliocentric model is closer to the correct model. We know now that it's not absolutely correct, but if you have idea, you have to prove it. You have to measure something to show other people that you're correct. So how to do it? At that time, they have only, of all astronomical instruments, they had only a stick and something like that. Only astronomer of those times can do was to measure angles. And here you see some instruments that are used to measure angles between the object and the star in the sky. The one is very sophisticated stick with something like with bars on it, and you move it from one point to the other and you can measure the angles. After some time there are some optical instruments and so on, but all those instruments were used only to measure the angles in the sky. And from the historical point of view, Kepler's law were formulated before the discovery of the telescope. It was based on the observations made by Tycho Brahe. You will see it later in more details, and it was before Galileo used the telescope for the first time in astronomy. So they can measure only angles using their eyes and something like that. If you don't have a proper stick, you can use your hand. Just this. It shows you approximate angle in the sky. So maybe you wonder now what we can do with angles. First thing, again from the history, is the measurement of the radius, the size of the Earth. Of course, you know how it was done, first time in the history, but let's think about something more astronomical, something we can do now. And here is an example. This is an example from the program Stellarium, but it's very easy to do it outside. Only thing you need is, let's forget that we have internet, we know where we are, and so on. Only we have to do is to measure the angle of polar star, our latitude. And this is the simulation of it. Of when, on Sunday, when I start to travel from Niš to here, let's get the angle of the polar star. It's same always, of course, but in Niš it's 43 degrees, something like that. And let's measure the angle here of the polar star in Thessaloniki. We are here and here. We are happy that the distance is mostly in direction of north-south. Because if the first city is something like this and this here, it will not work. But in this case, we can approximate that it's straight line from the north to south, and we can use this data. There are a lot of equations in this presentation, but you can ignore them, most of all, except the three of those equations. And we just use this angle, difference between two angles, it's almost 3 degrees, and this distance. You can measure it by plane or from the Google or travel by land. Of course, this result is not very good. And in the same way the Earth was measured the first time, we do it now. We have angle, we have the length of this arc, and we just divide and we can get the size of the Earth and the radius of the Earth. You can see that it's not much different than the real size. And of course, it's very simple, and we use very precise measurement from the stellarium. If you do it outside, maybe it will not be so precise, but it will work. And at first time when the Earth was measured according to these angles, it was not results what was important. The idea was important. The idea that the Earth is round, it's not flat. So at those first times, maybe you can compare the results. It's good, it's better, it's not so good, but the idea were important. Now we can do it even in school much better than this. And this result is if I measure the distance traveling by road, something like this. Of course, the result is not so good. So the angles are very powerful, and everything we measure in astronomy is in some way related to the angles in the night sky. And the beginning, or we can say the end of the astronomy, was the work of Tycho Brahe. Why the end? Because he was the last observer from the period before telescope. He was the last great astronomer that worked and collected many data, many good data, before Galileo used the telescope for the first time. And we can say that he was the beginning because he was the first real observer who collected data systematically with some plans and so on. So Tycho Brahe was the beginning of the observational astronomy as we know it today. And he was a strange guy, like, let's say. You have some information in the slide. I will not repeat everything. But this one here is his nose. His nose was an artificial one because he liked science so much that he lost his nose from the sword, because of the mathematical error from his friend. And there are a lot of stories about his nose. And in 2020, the body of Tycho Brahe was exhumated to check some facts. First, they checked what the nose were made of. The first idea was it was of gold, but it's not. It's some cheaper material. And there were some strange things about his death. There were some idea that he was poisoned from the material on his nose, and that he was killed in that way. And the second idea, second hypothesis was that he died because at some official event, he didn't want to excuse himself to go to the toilet. So they made some exhumation and solved some problem. And first is that he wasn't poisoned, and some research in that time showed that probably the cause of his death was the urge to go to the toilet. He didn't, and he didn't. So you will see later why this moment was important. And it is related to the Kepler. He was a great observer, and the beginning of his work was that he observed the total solar eclipse. He was fascinated by it, not by the phenomenon itself, but the way it was predicted. The error was 1 day, but he concluded that better observation will help us to understand and predict more precisely everything in the universe. Of course, he observed something very interesting. This, it looks like a plate of salad, is a supernova remnant. Of course, Tycho Brahe didn't see supernova remnant, but he saw a supernova explosion. He saw a new star that became so bright at the place there were no stars before. Of course, it was also a great event that helped him to choose astronomy and observation as his profession. And he was, let's say, a happy guy. He started with a small observatory, and after that he received the king's support. From the king, he received the whole island, only for observatory, only for astronomy. He was from the noble family, of course, and it was much easier than for the other people, but he had a great equipment and the whole fortress, the whole island, only for observational work and everything. It was a great time for Tycho Brahe, for astronomy of those times. About 20 years after he received the island, new king came and he lost his island. The son of the previous king didn't like Brahe, and Tycho Brahe left the island and went to the Prague. And the Prague is a place where the first idea of the Kepler's law arose. The Prague is a place where Kepler met Tycho Brahe, and the first time in the history of astronomy, theoretical and practical work were at the same place and the same time, and they worked to solve the same problem. Tycho Brahe was a great observer. He wasn't a good theoretician, but from his observation, he saw that something is not good with Ptolemy model. Observation and prediction of the model weren't in good correlation, and he was sure that something has to be changed. And the problem was he believed too much in previous model, in Ptolemy model, and made a little adaptation to a Ptolemy model. Sometimes, in most cases, you will not even hear about Tycho Brahe model, but again, we have Earth in the center, Sun that goes around the Earth, and all other planets goes around the Sun. So it's something between Ptolemy and the model of the solar system we know today. And this model is known, as you can see, geoheliocentric model. And here is Kepler. First theoretician in astronomy. As Tycho Brahe was first real observer, John Kepler was the first theoretician. He wasn't observer, and he just calculated. He wanted to calculate everything, but to check his calculation, he needed data, observational data, to compare the prediction of his results to the real world. And that's why the Tycho Brahe and Kepler are important, and if they didn't meet in Prague, I don't know what will happen. So Kepler, you can see many historical facts about him here, but the most important is this part when he met Tycho Brahe for the first time in Prague, and Tycho Brahe was skeptical about Kepler's work, but he gave him data for Mars, for the observation of the planet Mars, and it was for 2 months. Tycho Brahe guarded all others' observational data. He didn't want to give anything more to Kepler except the data for Mars. But it was very interesting for Tycho Brahe how Kepler worked on those data. He was fascinated by Kepler's idea and their way of work, his way of thinking. So there was some negotiation. Kepler went back home, and after some agreement, after a few months, they came back to Prague and continued to work with Kepler, and he had access to most of the data he needed in that time. And this is maybe the reason why the body of Tycho Brahe was exhumated and why there was idea that he was killed. 2 days after Tycho Brahe's unexpected death, Kepler was appointed as his successor and imperial mathematician. So there were some ideas, but of course there are a lot of ideas, but most of these historical ideas are not related to the reality. And after he became the imperial astronomer, there was a great time of the Kepler work. And those was the time when Kepler formulated his laws of motion. Here you can compare the main idea of Kepler's and Copernicus. Here you have a planet that goes around the sun in circular orbit. The sun is in the center, and the speed of the planet is always the same. It's the first heliocentric model, of course, and Kepler's law made a little difference, but very important difference that leads us to the solar system we know today, and we can really say to the universe we know today, because without Kepler's law, or we know now that those laws are only a consequence of Newton's law of gravitation, we cannot understand nothing in the universe, because they are very, very important. You know that probably that there are 3 Kepler's law, and the first one is very simple. The orbit of every planet is ellipse with the sun at one of the 2 focuses. You know that there are 2 focuses of each ellipse, and sun or the star is in one focus, and planet goes here. In orbital mechanics, in mathematics, there are a lot of parameters of the ellipse. You can see it here, and you can see how you can calculate it. Those are all parameters we need. A is semi-major axis, B is semi-minor axis, P is orbital parameter. We have coordinates, just normal coordinates, minimal and maximal distance, and so on. There are a lot of parameters. It's much more complicated than the circle, but it's not so complicated, and it is true. It works. And here how you can calculate those parameters if you know some of them. If we check what's going on with the first Kepler law, with observational data, here is the solar system. Almost all planets, orbits of all planets are almost circular. There are only 2 exceptions, Mercury and Pluto, that used to be a planet, now it's not, but let's put it here, and Pluto, of course, some other smaller objects. Why Mercury is very important? Probably you know that the planet Mercury was used to prove the general theory of relativity. And this is the reason why Mercury was a good candidate for this test, for this experiment. So it works very well. We can see it. And on this plot, you have eccentricity of some extrasolar planets we discovered up to today. You see that almost all orbits of the extrasolar planets are very close to the circle, but there are some extrasolar planets that ellipse is dominant one. The second Kepler law is a little bit complicated, and this is what it says. And a little bit of mathematics again, and the final formula. Maybe only this is not familiar. It's a so-called parameter mean motion, and it represents some connection between the motion, the speed of the planet that goes around the ellipse to the motion of the imaginary planet that goes around the circle. And it's just a speed that has for one full circle in time t. What's the main point of the second Kepler law? Maybe this image. This area, A and B, are same. If the planet is close to the sun, close to the star, speed must be higher. If the planet is farther from the star, the speed must be lower. And this is the reason, if you take when starts spring, summer, autumn, winter, and calculated the number of days for our north hemisphere, you will see some difference. You will see that winter for us is a little bit shorter than summer. This is because of this, because the speed is higher, and in winter the Earth is closer to the sun. Why we have to change the speed? Because of the gravitation. If the speed is too high, stronger than, we will not go much into the detail of physics, but if the speed is too high, planet will go southward. It will not go around the star. If the speed is too slow, planet will fall to the star. So you must have exact speed to keep the stable orbit, and you know gravitation is more powerful here than here. So the main point is that the speed changes and those areas A and B are equal for the same time. And the third, the Kepler law, is something like this. What we have here? We have this ratio. We have the ratio of object orbital period and its semi-major axis, and it's constant. At the bottom, we'll have some approximation with the circular motion, Newton gravitation, and so on, and this. Here we have that this constant is this number times in units, astronomical units and days. But if you look it better, you will see that this is nothing more than 1 over number of days in a year to the power square. Or if we get A in the unit in astronomical units and T in Earth years, we will get that this constant is 1 solar mass. So if we use appropriate units, this formula became very simple and very easy to use. Here we have some results from the Kepler, for the third Kepler's law, and his measurement data he used, and these are modern. So if you plot these two parameters, here you have just a straight line, as you expect from the equation. So what's the main point to use Kepler's law? The main point was to predict the position of the planet. And on the following few slides, you will have the whole algorithm with some not so complicated equation mathematically. You just use 4 basic operations, and if you know what trigonometric functions are, it's not very hard to compute it, but it takes some time, and it's straightforward process. It's very easy if you have an algorithm, if you know what to do. So we just compute this one. It's so-called mean motion, mean anomaly, eccentric anomaly, true anomaly. You have equations. What are those parameters? Those parameters tell us how much this orbit is different than the circle. All those parameters are here on this image. Here is the planet and its orbit. Here is the sun, and here is the circle around the sun. Of course, at the largest this distance, we have the intersection point of the orbit and the circle. So we have this point X, it's straight 9-degree angle is here, it goes to the planet. We have this blue and this blue area are same, and so on. So those are parameters that just tell us how much our orbit is different than the circle. And there is a standard way how to calculate it, and there are some constant you have to use. This one equation may be a problem. It's a so-called Kepler's equation. And when you have an equation something like this, it's not easy to solve it. In most cases, you have to solve it numerically, but that's some other story. But when you have numbers, you just put numbers in this equation, multiplication, division, adding and subtracting, and just follow the procedure. What will you calculate? You will calculate the radius, the distance, and the angle of the planet in the coordinate system. So easily we can convert it to something we understand more, to the Descartes coordinates, x, epsilon, and z. And we are in orbital plane. We are in a plane where only star and planet are. And now we have to move to the real coordinate system. And these two equations are just transformation of the coordinates, standard way again, but all we want to do is to find where our planet is at the specific time. So we just want to find where to put this dot. The center coordinate system starts here, and we want to find where to put the dot. Where is our planet in this x, epsilon, z coordinate system? It's standard way how to calculate it, and this was possible only because of the Kepler's law. Here we will try to do it, and those are constant you need. They're obtained in some different way. They can be find, so on. We will use it, and of course, it's 3D coordinate system related to the solar system. We cannot observe it. We can observe what we can see in the sky. So we must move the coordinate system to our point of view, and those equations do that. And what is the result? Of course, I didn't do it by hand. I made a computer program to do it. It's not very hard to do it. And this is the calculation from the Kepler's law and from the previous slides. And here is the exact position of the Saturn in that moment from the stellarium, of course, and you can go outside to check it if you want. There is a small difference because of some approximation and so on, but how big is this difference? If you use the stellarium, you know what these things are. You can just simulate the observational point of view for some combination of telescope and eyepieces, and I put the center of the point of view, or of the field of view, to the coordinate I calculated here, and here is the Saturn. The Saturn is in the point of view of the telescope. It's not very high magnification, and the difference between a prediction of the Kepler's law and this calculation is very small comparing to the real data, because here are more precise calculation and so on. So it was not so hard to use the research of Kepler to predict the Saturn, of course, if you know how to write the program, because calculating this by hand takes a lot of time. Now we will apply the third Kepler law to the something very famous, very well known to us, to the planet Jupiter. You can do it by your telescope. It's not, or binocular also. It's much harder, but here the simulation was done in program Stellarium. And what we will do? We will measure the distance between the Jupiter satellites, the most famous one, to the Jupiter, and use the Kepler's law to calculate the mass of the Jupiter. How we will do it? In some point of time, we will measure the distance between Jupiter and the satellite. You have a tool in Stellarium. You have to turn it on. That will help you do it, but there are some other way. You can get a piece of paper, for example. Maybe it's easier to get a piece of paper and to use a unit of Jupiter diameter as your units of measurement, and just measure how far from the Jupiter is this, and repeat it. The good thing is in Stellarium is that you can turn off daylight, and you can do it in a very short period of time. If you do it with telescope, of course, you have to do it only in nights. So you will have something like points here, but some empty space, but points, and so on. It will be much more complicated to get the results we want, but you can repeat this in Stellarium, and these are results. This is time. You read it from Stellarium. It's Julian date. It's much easier to calculate with it than the real date, months and years. This is difference between this, and this between this and this, and so on. The distance, Jupiter diameter, and the distance for the satellites from the Jupiter in the units of the size of the Jupiter, and some calculation of the units, and we will get something like this. It's very famous from oscillation, harmonic motion, mathematical pendulum, and so on. You can recognize it, and this is what's happening. But what we want to do now, we want to find a real mathematical function that in best way approximate these points. You can use specialized software for this. There are a lot of those softwares, but you can also use it by hand. You can calculate it by hand this is standard equation, basic equation, and you have to calculate these parameters. It's simple: maximum plus minimum, minimum, divided by 2, difference divided by 2, and the period. And we just calculate how this cosinus curve look like. Those are main parameter, and we have to determine those parameters approximately from our observation. You cannot make a big mistake. You just approximate everything, and you can try it. You see that this red line from this calculation is not so good, but you will see what's the final difference from the real results. Of course, if you know more about computers and mathematics, you can use some free software like this one, C. Davis, with standard procedure, with standard function, and this is the green line. And I did it here, and these are results. This is the first wave, paper and pen, and the mass of the Jupiter is 0.0009 solar masses, and this program, again, mass of the Jupiter is 0.009 mass of the Sun. Of course, the other decimal places are different, and the real results is here. So with very simple method, with very simple simulation, you can do it from the binocular. Of course, if you do it with the telescope or binocular, it's much more complicated to measure the distance between the satellite and the Jupiter. But it can be done. You can find a way how to do it. So you can just determine the mass of the Jupiter. Same procedure goes for the Saturn, and so on. And not just a planet from our solar system. You can use this method for extrasolar planets, because the telescope, space telescope that was used to discover most of the extrasolar systems we know today was named after Kepler. It was Kepler Space Telescope, and as you can see here, Kepler discovered 2070 and a little bit more confirmed exoplanet, and you see how much exoplanets are still candidates. The discovery wasn't confirmed. And if you get data for exoplanets discovered by Kepler and other missions, most of all by Kepler, you will, again, the third Kepler law, again, all planets are almost on a straight line here. Why is it important? Because you can do something like this. This is the light curve of one transit of exosolar planets. You know that planet goes around the star, and when the planet transits the star, like a transit for Mercury or Venus on Earth, there is a little bit change in the brightness of the star, and we can measure it. So from here to here is one period of the planet around the star. So you'll have this T, you have time for the third Kepler's law. But we don't know everything. We maybe don't know this and maybe don't know this. But we can find the mass, approximate mass of the star. Because from the spectral classification of the star, you just look at the spectra, you can recognize the type of star of everything, and all stars are classified in some classes, O, B, F, and so on. And for each class of the planet, you have approximate mass of the star in solar masses. So if you just put the data from here when you classify your star, you can determine the distance for the planet from their star. So again, you can use the third Kepler's law. And finally, we are at the center of the Milky Way, at the supermassive black hole. And this was discovery that was the reason for one of the Nobel Prizes in physics. And it was well known that Sagittarius A star is a strong radio source, and it was a very good candidate for observation and so on, but to observe something that's so far away and something that is in the middle of the galaxy, because you know that in the middle of the galaxy there are a lot of stars and it's very hard to observe. You have a very good telescope. You must use the best telescope in the world we have and the best technology you can find. So it was done, and most important thing is that the point of this is not to observe the black hole. It came after many years to observe and take a photo of the black hole in the center of the Milky Way, but they observe the stars that goes around the center of the galaxy. Because you know, if you have a black hole, it's black. You cannot see it. You can see what's going on around the black hole, and in that way you can conclude that in the middle is the black hole. But you have to observe something that you can see and use the laws of physics and calculate everything you need to conclude that in the middle is the black hole. And it was done from the results of this observation, because the most famous one is star S2. And why it's so important? Because its period around the center of the galaxy is about 16 years. For Sun, at our distance, is about 20 million years. So if period of the star is 16 years, it's very easy to observe the whole orbit. And this is it. Those are results from the observation of the star S2. And this observation were the reason for the Nobel Prize in 2020. This and all other stars. These are other stars that goes around the center of the galaxy, and analyzing this, observing, you can determine the mass of the supermassive black hole. And even you can try, following the algorithm from the presentation, to calculate the mass of the supermassive black hole using the observation, the data for this observation, and of course, Kepler's law. It's very easy to find, if you know where to look, to find data, for example, for this S2 star. It's one of the databases where those data can be found, because in astronomy, it's very nice that many data are freely available to everyone. Of course, great experiments, large experiments, have some time that they only use data obtained from those observations, but after some time, many of the data are available to the public, and you can do a research, or you can play with the data and learn something for the future. You can use real data to repeat some observation, some calculation, and after that, when you learn something, you can use those knowledge for next analysis and for real science. So here you have an algorithm, and these slides should be written somewhere. Try this at home. You have the whole procedure, how to use this data, this observational data, those are positions, for the star S2. The center of the galaxy is here. This is the orbit. So first, you have to plot this diagram to get this ellipse, the orbit of the star, and after that, you have to calculate everything using the Kepler's law. The area, now you can just use these lines for the point in time you have, then calculate this area, determine the speed, and so on. So if you follow this algorithm line by line and calculate it, and of course draw something you have, you can determine the mass of supermassive black hole in the center of the galaxy. So you can try it. And the most important thing that's not related to the astronomy maybe, but to learning, is that most of data, most of information, you can find very easy on internet or ask ChatGPT. So the most important thing is not to listen, not to memorize, but to learn to think and do things. Here, you have the results from one paper we did. It was published this year, but results are obtained in April last year for the first version, one of the first version of ChatGPT. We tested the artificial intelligence and compared the results with the results from the exam of courses on astrobiology. And as you can see here, the answers received from artificial intelligence were much better than the answers from the students. So you can maybe find everything on internet, but the main thing is to learn how to use those data. And it's interesting that, of course, it was one of the first version. Now this will be close to 100, but there is one important thing. If the ChatGPT tells you the wrong answer, it will be very sure that it is correct. So you must find a way how to check it. So the main point of study today is to learn how to check facts you can find and how to apply them to do something you need. So everything you see, everything you hear, you have to check and you have to try at home. So like this supermassive black hole, everything you can see, you can try to calculate and follow the results. And all those equations in the previous slides, maybe only these three are important. And let's say maybe the last one, the third Kepler's law, is the most important. Thank you.
Yeah, it's lunchtime, so maybe you will have the chance to discuss with Milan a bit later. In fact, we have a quite dense program for today, so now we will have the lunch break. Then we will have the two workshops. One will take place here. It includes the construction of a radio telescope, and then you will have the chance to test it outside. While the second workshop, which is related to the presentation of Milan and is going to introduce us, let's say, to the first steps of Galileo towards his discoveries, will take place at the computer room. So I will give the floor to Kostas now to announce to you how the two groups will be separated. We will follow this separation for the whole week. So make sure that you are always following the specific group.
Θα διαβάσω κάποια ονόματα στα ελληνικά. Αναγνωστόπουλος, Αποστολοπούλου, Μπαδιώτα, Μπαρούδας, Γενικόπουλος, Δελής, Διονυσόπουλος, Ευθυμίου, Επιτρόπου, Γανιάς, Γιαλούρης, Γκουγκουλιάς, Καϊάφας, Καϊμάκης, Καλιγάς, Κατσιούλη, Κοιάκος, Κουκούλης. Δεν θέλω να μου ζητήσετε καμία αλλαγή. With the students from the other Balkan countries will follow Mr. Pediotakis. Get up, please. Present yourself. To the library. Okay? The other Greek students will stay here after the lunch break. Is that clear? Okay. Now, let's go to lunch. We have only 30 minutes. Εντάξει, λίγο να τα πάμε. Έχουμε δουλειά, έχουμε κουρασιέρα.